Okay, so now we're going to try to make the connection between moles and the numbers that we actually see on the periodic table. So we said that the number underneath the symbol for the elements is the atomic mass or the atomic weight for the elements. And remember, that is the average mass of a carbon atom or a nitrogen atom or oxygen, whatever, in the units of AMU. Now, the way that that number is going to make more practical sense to us is instead of looking at individual atoms, which is very difficult to do, we can now look at moles of atoms. So, for example, if I have 1 mole of carbon atoms, we know now, right, that uh, I have a certain number of those, which is Avogadro's number, 6.02 times 10 to the 23 carbon atoms. The way that the periodic table is going to be helpful to me here is that if I have a mole of carbon atoms, I can look up the mass of that mole of carbon atoms. I can find that on the periodic table. So for carbon, a mole will have a mass of that same number. So it's the atomic mass number that you see, the 12.01. But the interesting thing now is that we just changed the units to grams. So a mole of carbon atoms will have a mass of 12.01 grams, and then it will be of carbon. It is that simple. So we just by having access to the periodic table, you automatically are going to know what the mass of 1 mole of any of the elements are. And the mass of 1 mole of something, 1 mole of anything, we refer to that as the molar mass. So the mass of 1 mole of anything. And for the elements, okay, all we need to do is to look it up in the PT, the periodic table, right? It's the same number as the atomic mass. We just changed the units to grams of it. So molar mass, mass of a mole of anything for the elements, as long as you have a periodic table, and you'll always have one, got one in lab last week, keep that with you as you take your quizzes and exams. The masses for all, the molar masses for all of the elements are on the periodic table. So for instance, if I have a mole of oxygen atoms, right, 1 mole of oxygen will have a mass of, so a mole of oxygen atoms have a mass of 16.00 grams, right? And it's a lot easier to measure out grams of things than atomic mass units of things, right? It's like I said, it's very difficult to do that. So what allows us to do it is the fact that we're dealing with moles of things now, right? And moles, again, is Avogadro's number. That's a little bit more, a little bit easier to manipulate than individual atoms or individual molecules. So because the molar mass relates the mass of 1 mole of anything, um, we can use it to convert between moles and mass in grams. So for example, if we use the carbon, one that we had before, okay, 1 mole of carbon atoms is equal to 12.01 grams, right? That's not something you have to memorize. You look it up on the periodic table. So if you're given, let's say you measure out let's say 45.75 grams of carbon in the lab. Okay, how many moles of carbon is present in that sample? Okay, so now what we're given here is grams. So we're given grams or mass of C. We want to convert that into moles. of C. So we're going from grams of something to moles of that thing. So we're going to use the molar mass. Okay, and that molar mass says that 1 mole of carbon in this case, look it up on the table, 12.01 grams of C. Right, that's my relationship. I'm starting off with grams of C, so I'll have 45.75 grams of carbon. I want to convert that now to moles as my final unit. So I'm going to put that on top, whatever unit you want needs to go on top. So 1 mole of carbon atom has a mass of 12.01 grams of C. Grams of carbon go away. What I end up doing here is dividing 45.75 by the 12.01, the molar mass, and we end up with 3.8, how many sig figs? 4 sig figs, 3.809 for my unit moles of carbon. What I could also do is incorporate the previous relationship into this, and I can also convert the moles of carbon into number of carbon atoms. So if I want to go from moles to number of atoms, here I'm going to use Avogadro's number. Okay, and this is something we did a couple times before. So if I have my 3.809 moles of carbon, I know that for every 1 mole of carbon, 1 mole of anything, I have Avogadro 6.02 times 10 to the 23 carbon atoms. Moles of C go away, right? So I end up multiplying 3.809 times 6.02 times 10 to the 23. So I get 2.29 times 10 to the 24 carbon atoms. All right, so I can go from, if I wanted to, if I have the mass of a sample of an element in grams, I can calculate how many of those atoms I have by first of all going through moles of that thing and then using Avogadro's to get to number of atoms, right? So I can go from grams, let's say mass of the element. I can convert that to moles of the element. And then I can convert that into grams of the element. I'm sorry, we started with grams. We're going to convert that to number of atoms of the element that we have. Right, and what allows us to convert these, right? Those are the relationships. So going from mass to moles, we're going to use the molar mass. And get that from periodic table. To go from moles to number of things, we use Avogadro's number. And we can go in this direction from left to right. We could also go in the opposite direction as well, going from number of atoms to moles, then moles to grams. By using the same relationships, we're just going to flip them when we do that. All right. So yes, there's some math involved in this, and the way that I've set it up makes use of the dimensional analysis or the factor label method. You can do it alternative ways if you want, but the key thing here is that you're using the right relationships, right? To get from one thing to the other thing. So we're looking at how we relate moles to masses for the elements, for the atoms. What about if we had bigger things, like maybe some of the compounds or the molecules? Well, we can apply the same thing to larger and larger particles. So we apply the same concept to larger. So let's use, I think we'd use water before, right? So we said that one H2O molecule, okay, is made up of two hydrogen atoms. Okay, and then we had one oxygen atom in it as well. So what I can do is I can actually find the mass of one of these water molecules. So one water molecule then would have a mass of 2 times the mass of hydrogen and 1 times the mass of oxygen. I can look these up, right? Hydrogen is 1.008. I have 1 times oxygen, 16.00. So I add these up. What do I get here? 2.016 plus 16.00. So that gives me 18. We're going to round it 0.02. And then this is atomic mass units. All right, so all I'm doing is I'm looking up these values here, these atomic masses from the periodic table. So I'll just show you really quick, remind you where those are. For hydrogen and oxygen, hydrogen is over here, and then oxygen over on this side. So for molecules, right, I can calculate the mass of an individual water molecule, right? So this is saying one H2O molecule, if you were so inclined, and if you had the right tools, you could possibly, with a lot of effort and expenditure of energy, you can measure out the mass of a water molecule as 18.02 atomic mass units. Now, it's more realistic to work in moles, as we said before. So if I have a mole of H2O, right, that means I have 6.02 times 10 to the 23 H2O molecules. And it just so happens that if I have a mole of H2O, and I calculate the mass of that sample, it's going to be the same number, 18.02, but now the unit here is just going to be grams of H2O. And this is the molar mass of, in this case, water. Right, so the mass of 1 mole of water is 18.02 grams. Another way of looking at this is to say, if I have a mole of H2O, right, this means that it contains 2 moles of hydrogen and it contains 1 mole of oxygen. All we're doing to get these mole to mole sort of ratios, we just look at the subscripts from the formula. Just like we use the subscripts to determine how many individual atoms we had in the molecule, right? So that those ratios, yes, they tell you in what ratio the atoms combine, but they also give you a mole to mole ratio, right? And we use the same. We know that the molar mass for hydrogen is 1.008, and then that's grams. The molar mass for oxygen, 16.00 grams. Now we add these, we're going to get the same number, right? 18.02. Now the units is grams. So we can calculate, we can actually look up the individual molar masses for the elements, and we just incorporate them, we combine them, taking into account the subscripts to calculate the molar mass for any compound, whether it's different types of compounds. In this case, we have molecules, molecular compounds. It's the same idea. Let's take a look at another example. Let's say I'm going to calculate here the molar mass of a very, very important molecule or substance called glucose, which is a type of sugar. It's what your body burns for energy. And glucose has the following chemical formula. It's C6H12O6. So it's fairly large, especially when you compare it to like H2O. But that's really irrelevant. As long as you have the correct formula with the right subscripts, you can calculate the molar mass for anything, right? And again, you need a periodic table, but all we're doing is reading the subscript. So this tells me that I have 6 carbons, I have 12 hydrogens, and I have 6 oxygens, right? All I'm doing is reading the subscripts. I'm going to look up their molar masses from the table. So I have 6 times carbon. Let's see, carbon here is 12. We did that one already. So it's 12.01. all the way up here. So 6 times 12.01, and then that's grams. Now we're looking at molar masses, so the units have to change. 12 hydrogens, so hydrogen is 1.008, and then the 6 oxygens, each oxygen is 16.00 grams. So we add these together. What do we get? 12 sixes are 72.06. We get 12.096. 16 by 6 is 96. These are all grams. We add these together. Okay, and we're going to get what? 5, 1. And then 0, 9, 80.156 grams. So what this is saying, right, is that 1 mole of glucose has a mass of 180.1, or rounded to 2 decimal places, 0.16 grams of glucose. Right, and you can calculate the molar mass for anything. As long as you have the right formula, as long as you have a periodic table, we can look up these values. Right, so these here we look up on the periodic table. So we can use that relationship like we did before. We can say now if I have moles of a compound, I can use the molar mass to convert it. Oh, let's back up a second. If I have grams of a compound or mass, I can use the molar mass of that compound to convert it to moles of the compound. And once I get to moles of the compound, I can convert it to number of whatever we're doing this. So let's actually use the word molecules here. We've been using molecules all along, so we'll use that type of compound. So mass or grams of the molecules to moles of the molecules, and then we can use Avogadro's number to convert it to number of molecules. Okay, so for instance, and again, we can go backwards as well. We can go from number of molecules to moles by using Avogadro's. We can go from moles to grams by using the molar mass. So let's put that into practice. Let's say a sample of glucose contains a fair bit. So let's say 1.35 times 10 to the 25. Let's say 24. It's 10 to the 24 glucose molecules. We define two things. How many moles of glucose is present? And then secondly, what would be the mass of the sample? Okay, so in our first step here, we want to convert, we're going from, what's number 1, 2. So in number 1, we're going from number of molecules. We want to go to moles of that thing. So we're going to use Avogadro's number, right? So we're given 1.35 times 10 to the 24 glucose molecules, and then I'm going to use Avogadro's number. So if I want to end up with moles, right, as my unit, I'm going to put moles on top. Avogadro says that for every 1 mole of something, in this case, glucose, okay, I have his number, 6.02 times 10 to the 23 glucose molecules. Okay, so the glucose molecules go away. So I just end up dividing, right? The 1.35 times 10 to the 24 by 6.02 times 10 to the 23. Let's put that in. And again, you know, having good calculator skills is going to be very important for this. So 1.35 times 10 to the 24. We're going to, oops, 1.35 times 10 to the 24. And then that's divided by 6.02. So Avogadro, 6.02 times 10 to the 23. And that's going to give us 2 point, let's see how many sig figs, 3 sig figs, 2.24. Then my unit here is going to be moles of glucose. Remember, generally, when you're dealing with moles of things, the actual value you get tends to be fairly small compared to the number of molecules, the number of atoms, which always are a lot larger. All right, so that's the first part of this. We can convert from molecules to moles, and then the second part going from, we want to get to the mass of the sample. So to get to the mass, we need the moles, which we just found. We're going in this step now. We're going to use the molar mass of glucose, which we calculated before. So using what we got from the previous step, 2.24 moles of glucose. We'll put that over 1. And then our molar mass for glucose says that for every mole, let's see what it says up here, that we calculated it. Okay, so I want the moles to cancel out. I want to put the grams on top because that's what I want to end up with. So I have moles, 1 mole of the glucose is 180.1, whatever, 6 grams of the glucose. Moles go away. So 2.24 times 180.16 would give 403. And then my unit grams of glucose. Okay, so the same steps, the same general steps that we used to convert moles to grams to number of atoms that we saw up above. Okay, mass to moles to atoms. The same steps that we use using molar masses, Avogadro's number, we're applying those same 2 concepts to molecules now, right? It's the same idea. We're just transposing it into a different setting. So as long as you have a periodic table and the correct formulas, we can calculate molar masses very easily. That allows us to go now from mass to moles of anything. Okay, and then one last thing, when we calculate molar masses, or in some cases if you're given, let's say in a question, if you're given the molar mass of something, sometimes it's shown in a slightly different way. So let's address those because you will see this occasionally. So molar masses are sometimes represented as follows. So we just calculated the molar mass of glucose, right? So, and that you can calculate it, but sometimes you'll be given molar masses. So for glucose, we know that 1 mole is equal to 180.16 grams, right? Alternatively, we can say the molar mass for glucose is 180.16 grams per mole, right? That means the same thing. It means that for every 1 mole of glucose, we have a mass of 180.16, or sometimes you'll see 180.16 grams times moles to the -1. Okay, that is the same. There's nothing different about that compared to the one before. It means the same thing. So when you are presented with molar masses, this is usually how it's going to be presented to you, right? And you need to take that information and turn it into a form that you can easily use, right? So, and expressing it as an equality, I think, is a much more user-friendly way. That way you can set up your conversion factors, see how the units canceled, and so on and so forth. So keep that in mind as you're working through some of these problems involving molar masses.